Welcome to ITT Industries' Little Red Schoolhouse, a fully equipped learning center that has graduated over 45,000 students since opening its doors in 1954. Graduates from every state in the Union and most countries on the planet. The subjects taught here vary greatly, but are designed to teach engineers, contractors, and installers about the proper design, installation, and maintenance of hydronic and steam systems. Hi, I'm Roy Algren, and today we're bringing the Little Red Schoolhouse to you. We hope to show you some things that will help you in understanding hydronic systems a little bit better. This is our pump compression tank location demonstrator. We use it to demonstrate the importance of the location of the pump in the compression tank, particularly if it's a high-headed pump. And here to take us through this important demonstration is Gil Summer, one of our schoolhouse instructors.
Thank you, Roy. Let me start out by saying all the pump does is circulate the fluid in the system. The point at which the tank is connected to the system is the point at which the tank exerts its pressure on the system. The pressure at that point cannot change unless the pressure in the tank changes. The pressure in the tank can only change if the proportions of water and air change. The pump cannot change the pressure in the tank because the pump cannot change the proportions of air and water in the tank. Consequently, pumping toward the tank or away from the tank will not change the pressure at that point, but there are some other ramifications. If the tank is connected closely to the pump suction, when the pump operates, all of the pump head will show up as an increase in pressure throughout the system. The head is used to overcome the piping resistance. The pressure then at every point in the system is higher with the pump running than it is with the pump off. However, if the tank is connected closely to the pump discharge, a strange thing occurs. The pump can't change the pressure at the discharge. Consequently, being a one-trick pony, all it can do is reduce the pressure at the suction. When the pump is in operation then, the pressure in the system is lower at every point than when it is with the pump not operating. If the head of the pump is greater than the non-operating pressure in the system, at least part of the piping system will operate in a vacuum. An automatic air vent installed in an area with a negative pressure will suck air into the system. Not a welcome occurrence. Since seeing is believing, hopefully the following demonstration will solidify your thinking on this problem. This is a 1522 pump with a head greater than the non-operating pressure of the piping system. It also has a closed piping system. The tank has a gauge which is connected to a manifold which enables us to connect the tank to the pump discharge or the pump suction. We have a large pressure gauge. We have a large compound gauge on the suction side. We have sight glasses which can be lighted, which will show us what happens as we change the location of that tank from the suction to the discharge. First, the tank is connected to the suction. With the pump not operating, all of the gauges read the same 12 psi. When the pump starts up, the pressure on the tank and the pump suction remain at 12 psi. The pressure at the pump discharge goes to 32 psi, which reflects the head of the pump, 20 psi or 46 feet. Importantly, both of the sight glasses remain clear. Now let's turn off the pump and change the location of the tank from the pump suction to the pump discharge. Again, with the pump off, all of the gauges read 12 psi. Once we start the pump, you'll notice that the pump discharge and the tank pressures remain at 12 psi, but the pump suction has dropped to 13 inches of mercury. The difference between the pump suction and pump discharge is equivalent to 46 feet the head of the pump. Note that the sight glasses are no longer clear. Air has come out of solution and the bubbles are easily seen. The amount of air that is soluble in water depends upon the temperature and pressure. Air is more soluble at higher pressure or lower temperature. This demonstration clearly shows the importance of locating the tank at the pump suction. To summarize, free air, which can be caused by a drop in pressure, can air bind circuits, can cause noise, can even cause cavitation. This demonstration clearly shows that simply hooking the tank up to the pump suction eliminates that drop in pressure, which prevents air coming out of solution, causing noise, causing cavitation. Here's hoping that this demonstration will prove beneficial to you in your future endeavors.